Over the next 3 videos we're going to learn about determinants of square matrices. You've already seen 2x2 and 3x3 determinants on various videos in this course. Here's the definition of the determinant of an arbitrary n by n matrix. If its ij entry is lowercase a subscript ij, then the determinant of A, which we write like this, is defined to be the sum over all permutations S in Sn of the sign of S times a1 s of 1 times a2 s of 2 up to an s of n. Before we do anything, let's make an important observation about the definition of this determinant. Each one of these summands contains exactly one factor from each row of A. So this term is from row 1, this term is from row 2, and this term is from row n. But also it contains exactly one factor from each column of A, because the numbers s of 1, s of 2, s of n, which control which column these factors are from, are just the numbers 1, 2, 3 up to n in some possibly different order, because S is a permutation. So the determinant is a sum of products, and in each of those products contains one term from each row of A and one term from each product from each column of A. To get the hang of determinants, let's look at some small cases. For n equals 2, I'm going to draw a table where on the left is a permutation S, and on the right is the corresponding term in the sum defining the determinant. There are only 2 permutations in S2, the identity and the transposition 1, 2. The identity is even, so the term in the sum comes with a plus, and what I should have is a1 s of 1 times a2 s of 2. For 1, 2, that is an odd permutation, so it comes with a minus. Then I have to have a1 s of 1 times a2 s of 2. You can see that when I add the 2 terms in the right-hand column of my table, I do get the expression for the determinant which I claimed in the example box. Let's do a couple of examples for the 3x3 determinant as well. Again, on the left I will put a permutation, let's say 1, 2, 3. And on the right I will put the corresponding term of the determinant. 1, 2, 3 is an even permutation, so I get a plus. Then I should have a 1 s of 1, a 2 s of 2, a 3 s of 3. That really is one of the terms in the determinant that I wrote in the example box. In fact, it is this one. Let's just do one more, so we'll do the permutation 1, 3, which is an odd permutation. So its term in the determinant comes with a minus sign. Then I have to have a 1 s of 1, a 2 s of 2, a 3 s of 3. Again, you can see it right here in what I claimed was the determinant. The determinant has lots of useful properties, and perhaps the most useful of all is what's called the row linearity property. The notation here is that these things which are called R or R prime are row vectors. Those represent the rows of some matrices. On the left-hand side of the claimed equality is the determinant of a matrix whose rows are written as R1 up to Rn, except in position I, I've got a linear combination of 2 row vectors. I've got Ri plus L times Ri prime. Here Ri prime is just another row vector of the same size as the other Rs. It's got no relation to Ri at all. And L is just some number. Then on the right-hand side of this claimed equality is the determinant of the matrix whose rows are the Ris, or rather the rows are R1, R2 up to Rn. And the second term is L times the determinant of the matrix whose rows are the Rj's again, except that in position I, I've got Ri prime. The proof is really a simple application of the definition of determinant, which I will remind you of right here. Remember, the definition of the determinant of a matrix whose ij entry is Aij is the sum over all permutations S in Sn of the sign of S times a1 s of 1 up to an s of n. So if we introduce some notation for our row vectors. We'll write Ri as ai1 up to ain, and Ri prime as a prime I1 up to a prime in. Then we can express the determinant on the left in the following way. It's the sum over all permutations s and Sn of the sine of s times a1 s of 1 up to the term from row I, which will be ai s of I plus L times ai prime s of I. That's because row I on the left is Ri plus L times Ri prime. And then we keep going with aij's up to an s of n. Now just multiply this out. So multiply out the brackets. What do you get? Well, the first thing you get, so the term which arises from the first term in brackets when you multiply out, is exactly the determinant of the matrix whose rows are the Ri's. So the first term obtained by multiplying out the brackets is precisely the first term on the right-hand side of our claimed equality. Now think about the term which you get when you multiply out the second, the term which arises from multiplying out those brackets, arising from the second term inside the brackets. Each one of those terms will have a factor of L, so we'll pull the factor L out to the front of the sum, right here. Now what the term that you get will look like is a1 s of 1 up to ai minus 1 s of I minus 1, and then the row I term would be ai s of I prime. Then you keep going from ai plus 1 s of I plus 1 up to an s of n. Well, that is precisely L times the determinant of the matrix whose rows are R1 up to Ri minus 1, and then Ri prime, and then Ri plus 1 up to Rn. In other words, the matrix whose determinant is the second term on the right-hand side of our claimed equality. So we're done. Another important property of determinants is called the row swap property. What it says is that if you swap two rows of a matrix, then you change its determinant by a factor of -1. To make this easier to write down, let's introduce the row operation R, which swaps row P and row Q. Then what we're claiming is that the determinant of R of A is equal to minus the determinant of A for any square matrix A. The proof works by a really simple property of sums. Let's say you have two additions, x plus y and z plus w. And let's say you know that y is equal to minus z and x is equal to minus w. Well, all right, then the first sum is minus the second one. So that's how we make our proof work. We're just going to pair up the terms in the determinant of R of A and the determinant of A, and observe that under the pairing that we choose, the term in the determinant of R of A corresponds to a term which is minus that value in the determinant of A. So let's do it. Here is our matrix A. We're going to let its ij entry be Aij, and we'll let the ij entry of R of A be A prime ij. So the precise expression for A prime ij in terms of A prime is that A prime ij is equal to Aij, except A prime pj will be A qj and A prime qj will be A pj. Now let's think about a particular permutation S in Sn. So A here is an n by n matrix. So that term would involve a sign, the sign of S, multiplied into the following product. So you would have A1 S of 1, A prime 1 S of 1 rather, times A prime 2 S of 2, and at some point you see A prime P S of P, and you see A prime Q S of Q, and finally you end up with A prime N S of N. So this is part of, because it's missing the sign, the S term of the determinant of R of A. That's what I've written down on the left-hand side of this equality. Now, let's translate this product into a product just with A's and no A primes in it. As we've seen, the only difference between the A's and the A primes is that A prime Pj is A Qj and A prime Qj is A Pj, because we swapped rows P and row Q. So when we translate the product on the left into a product of A's, the only difference is that A prime P SP will be A Q SP. So this term is equal to this term. And equally, A prime Q SQ will be A P SQ. So what you've got on the right there is almost the term in the determinant of A, missing its sign, corresponding to the permutation P, S. But it's not quite right, because after 1 you've got S of 1, okay, and after N you've got S of N, that's also right. But after P you've got S of Q, and after Q you've got S of P. So actually what's happening here is that the term you have here, this belongs to the S composed with the transposition PQ term, or summand, of det A. So the term on the right appears in the summand of the determinant of A corresponding to S composed with PQ. So the way we'll pair up the terms in the sum defining R of A, the determinant of R of A, and the terms in the sum defining the determinant of A, is we'll pair up the S term in the determinant of R of A with the S composed with PQ term in the determinant of A. What we've seen in our equality is that those terms have the opposite sign, because the sign of S is minus the sign of S composed with PQ. It's got one extra transposition. But apart from that, they're equal. So this gives us a way to pair up terms in the two determinants such that the two terms that we pair up are opposite in sign, and therefore the two determinants are minus one another.